Hi everyone! In this video, I'll show you the solutions to the homework problems from Class 5, Number Theory, Factors, Multiples, and Bases. Remember, if you haven't already watched the video, make sure to go watch it, as many of the concepts there are crucial to solving these problems. Also, make sure to try these problems beforehand, as trying the problems can give you more insight in how you can also understand the solution better. Now that you've done all those things, let's start off with the solution to the first problem. The 25 integers from -10 to 14 inclusive, so we're including all the bounds, are to be arranged to form a 5 by 5 square in which the sum of the numbers in each row, the sum of the numbers in each column, and in each of the main diagonals are all the same. So what we realize here is that what is the total sum of all the numbers? So what's -10 plus -9 plus all the way till 14? Well, notice that all the numbers from -10 to 10, they overall sum to 0. So we're really just doing 0 plus 11 plus 12 plus 13 plus 14, which will have a sum of, well, 50. So now that we know the sum of all the numbers in all the grids, so the sum of the numbers in all 5 rows are 50. So if each row has to have the same sum, remember, in each row we have that the sum of the numbers in each of the row is going to be all the same. And there's some other conditions, but we don't worry about those for now. So we have 5 rows. They each have let's say a sum of x. So let's say each of these 5 rows is a sum of x. And that means that 5x, the sum of the rows in the sum of all the 5 rows, each with the sum of x, is going to be 50. So the sum of each of the rows, or the common sum the problem asks for, is just going to be 10, or 50 divided by 5. That's the answer for this problem. Okay, now let's look at this problem. All the numbers 2, 3, 4, all the way till 7 are assigned to the 6 faces of the cube, one number on each of the faces. And what we're doing is for each of these 8 vertices, we're multiplying the 3 numbers on the 3 adjacent faces. So that's what the problem says. For each of the 8 vertices, we're basically multiplying the 3 numbers that are on the 3 faces, and we're to find the greatest possible sum of these 8 products. So how can we sum these 8 products up? Well, how can we maximize the sum is a real question to be asked. So the idea here is that one face is adjacent to exactly 4 other faces, right? So let's say, look at the face 7, for example. So the face 7 will be adjacent to 4 of the faces from 2 to 6, because there's 4 faces adjacent to every face. But notice that there are 5 faces from 6 to 2. So there's one face that must not be adjacent to 7, or that's just going to be the opposite face essentially. So let's just say that face 7 is on the blue face. Let's just say we put face 7 on the blue face. So I'm trying to make it clear as possible that this is a very front face, you can think of it as. So if 7 is on the blue face, or the front face, well then, what will be on the back face? That will be 2. So then we put 2 on the back face here. So now we know that 7's at the front, 2's at the back. Now we need to look at the sides. So now we have the numbers 3 through 6 remaining. So now we have 3, 4, 5, and 6 remaining. So we have 3, 4, 5, and 6 remaining to go on the 4 lateral faces on the outside of the 7. So the idea from here is that 6 is also a pretty large number. So essentially, in order to maximize the overall product, we want to multiply the large numbers by the large numbers, because a large number times a large number is even larger, whereas a large number times a small number is very small. So it's always better to multiply the larger numbers together and multiply the smaller numbers together, because multiplying the largest numbers together makes it even bigger. So we put 7 on the front, 2 in the back, because we don't want to multiply 7 and 2. Their 1 is big. We don't want to waste the 7 on the 2, which is so small. So we put 7 on the front, 2 on the back. Now we have the numbers from 3 to 6. So 6 is also a pretty big number, right? 6 is also a pretty big number. So what do we multiply by 6? So let's just say the 6 goes on the yellow face here. Let's say 6 goes on the yellow face to the right. So if 6 goes on the yellow face to the right, now we know that 6 is already being multiplied by 2 and 7. So now out of the remaining faces, 3, 4, and 5, we must choose one face for 6 not to multiply. And 3 is the smallest amongst all 3, so we don't want to multiply 6 by 3, because multiplying 2 smaller numbers is never good. So then we're going to go and put a 3 on the opposite face of a 6. And now we just put the 2 remaining faces, 5 and 4, on the top and the bottom. So the top face will be 5, and the bottom face will be 4. The reason I'm doing it doesn't really matter which order you put them in. It will result in the same product either ways. So now we just need to sum our product up because this is the maximum configurations. Because now we're multiplying all the bigger numbers like together in the we're multiplying all the bigger numbers together and multiplying the smaller numbers together. So this will give us the greatest possible product. So now what we need to do is we need to multiply all these possible products. So we're going to do 7 times 6 times 4. So 7 times 6 times 4 plus 7 times 6 times 5. And then we're also going to add up 7 times 7 times 3 times 4 plus 7 times 3 times 5. So we're just adding up 7 times 3 times 4, 7 times 3 times 5, 7 times 6 times 4, 7 times 6 times 5. And now what we can do is we can just add these all up together to get that. The overall sum for all the numbers we're multiplying by 7 is just going to be 7 times, and then we can simplify this out to get 9 times 4 plus 9 times 5, which is equal to 7 times 9 times 9. Okay, so that's what we're multiplying for all the 7s. What about the ones that are not including 7? So the only products that won't include a 7 are the ones that include a 2. Because the only products that won't include a 7 are the ones that have a 2. So what we can do is you can see that all the products with 7, there's also going to be the same products for 2. So we also have 2 times 6 times 4, so 2 times 6 times 4, plus 2 times 6 times 5, plus 2 times 3 times 4, plus 2 times 3 times 5. Because we're just essentially multiplying the same thing that we multiplied to 7, except we have 2 instead of a 7. And then just like earlier, we add this up to get 2 times 9 times 4, plus 9 times 5, which is just 2 times 9 times 9. So now overall our sum is just going to be 7 times 9 times 9 plus 2 times 9 times 9, which is just 9 times 9 times 9, or 729. And that's the answer for this problem. I know this is not like a completely rigorous proof, but it gives an intuitive idea. And if you're still a little bit confused on why this is true, just think about let's say adding the product 7 times 6 and then 5 times 4, vs adding the product 7 times 5 and then plus 4 times 6. And you can see that this one was clearly larger. So hopefully that gives you an idea of why multiplying larger numbers together will always be greater than multiplying the larger number and smaller numbers together. How many odd positive 3-digit integers are divisible by 7 but do not contain the digit 3? Okay, so we notice that we have these 3 slots and it's odd. So that means the last digit can be 1, 3, 5, 7, or 9. But never mind, because you have the digit 3 here. So be very careful on that. So actually there's not going to be any 3. So I'm just writing all, and similarly for this digit we can have 1, 2, 3, 4, 5, 6, 7, 8, 9, and a 0. But again, no 3. So we erase the 3. And then we also have, for this first digit here, we can also have anything except we cannot have 0 this time. So you can only have 1, 2, 3, 4, 5, 6, 7, 8, 9. Of course, excluding the 3. I'm just crossing out the 3 just to make it clear that we're not including the 3. Okay, so then what do we do here? Well, the idea here is that one way is casework, but that seems like it's going to be very, very annoying here. So we can just do casework on whatever the value of the third digit can do that. Or a more clever way is that we noticed and we try to take advantage of some symmetry here. So notice that there are 8 numbers in this column, 9 numbers in this column, and 4 numbers in this column. So you might just think the answer might just be, well, 288, right? Except that's not true. The reason it's not true is because we have this annoying condition here, divisible by 3. And, well, if you remember from the divisibility rules class from AMC 8, that means the sum of the digits has to be divisible by 3. So not all of these 288 ways work. So how can we deal with that condition? One way, like I said earlier, is to break it up into cases. Another way is to notice that there's some symmetry involved here, like I said earlier. So the idea here is that this has 9 possible numbers, right? So we have 0 and 6 and 9 that are all multiples of 3. We have 1, 4, 7, which are all multiples, 1 more than multiples of 3. And we have 2, 5, and 8, which are all 2 more than multiples of 3. What does that mean, really? Well, let me show you what this means. So basically, let's say we take any 2 numbers from the first and the third rows. Let's say we have 4 and then let's say 5. So if we have the 2 numbers 4 and 5, in order for the sum of the numbers to be a multiple of 3, the middle digit has to either be 0, 6, or 9. Because remember, no 3. So as you can see here, we have 3 possible values for the middle digit. Let's just take another example, just to make it a little more clear. Let's say, let's take 6. Let's say 6 and 1. Okay, 6 and 1. So if you're doing 6 and 1, now we see that 6 plus 1 leaves a remainder of 1 when divided by 3. So if the sum of the first and third digit has a remainder of 1 when divided by 3, the middle digit has to be 2 more than a multiple of 3. Meaning that it can be 2, 5, or 8. Again, giving 3 possibilities. This is starting to seem a little bit interesting. So let's take just one more example just to see where we really are here. Now let's take 7 and 4. Sorry, 7 and 1, let's say. So now let's say 7 is the first digit, 1 is the last digit. That means the sum of the first and the third digit is now 8, but just 2 more than a multiple of 3. Meaning the middle digit, in order for the overall sum of all the digits to be a multiple of 3, has to be 1 more than a multiple of 3. So that means it can be 1, 4, or 7. So again, 3. So now we see that there's 3 possibilities no matter what. So no matter what first and third digit we choose, there's always going to be only 3 values for the middle digit that works. The reason is that we have 9 possible middle digits, and 3 of them leave a remainder of 0 when divided by 3, 3 of them leave a remainder of 1 when divided by 3, and 3 of them leave a remainder of 2 when divided by 3. Meaning that for all possibilities, there's always going to be exactly 3 cases for the middle digit that make the overall sum of digits equal to 0. They have a remainder of 0 when divided by 3. And we'll actually learn modular arithmetic in the next class, so make sure to stick around for that. So that means that exactly 3 of these ways actually work. And exactly 3 of these ways actually result in a possible solution. So then we just do 8 times 9 divided by 3, or 3 times 4, which will give 96 as our answer. And that's the answer for this problem. And just to summarize the steps here, what we notice is that we look at the first and the third digit, we look at the possible values for that digit, and then we saw that exactly 3 possible values for the middle digit will always work, no matter the first or the third digit. So we just do 8 times 4 times 3 in the middle, and they get 96. And you might be asking, how do you think of that? Oh, we have to look at the middle digit from 3 possible values? Well, the idea here is that when we just try to avoid casework, because casework is very messy usually. So instead we can just look at the first and the third digit and see that no matter what we choose, you can see that the middle digit will only have 3 possibilities. You can just try a few examples like we did here, and that's how we'd come up with the fact that the middle digit will always have 3 possibilities. So now let's move on to the next problem. How many positive 2-digit integers are factored to 2 to 24 minus 1? So one option is just to expand this out and factor it, but I'm sure you're not going to have a good time doing that. So instead, let's look at the more clever way. 2 to the 24 minus 1 will be, well, what does this really think? Is there any way we can somehow, factorize it before we multiply it out and do a bunch of long computation? Well, notice that 2 to the 24 minus 1. So does this remind you of any factorizations that we learned in class 2 from the AMC 10? Which, by the way, if you haven't learned factorizations, you should definitely make sure to go check out the factorization videos from class 2 of AMC 10-12. So go check out. The video will be on this channel for you to watch. And we discovered many important factorizations like difference of squares, difference of cubes, sum of cubes, some of which we were actually going to use in this problem. So the idea here is that 2 to the 24 minus 1, is going to be equal to 2 to the 12 minus 1 times 2 to the 12 plus 1. Right? Because difference of squares. This is a minus 1, this is a plus 1. We get a squared minus 1. So we separated by difference of squares. So the reason is we're always on the lookout for even exponents. Even exponents or multiples of 3 exponents, because those gives us nice ways to factorize things, right? Okay, so next what we want to do is we want to see that, okay, now we've got 2 to the 12 minus 1, we've got 2 to the 12 plus 1. Now we want to factor this even further. We're going to want to make it 2 to the 6 minus 1, right? And then 2 to the 6 plus 1. Because again, we can use the same property. And from here we can do it again. We can just keep doing it. 2 to the 3 minus 1, 2 to the 3 plus 1. Times 2 to the 6 plus 1, of course, in the other terms. So now we've pretty much knocked down the first term. So now we're left with this very big 2 to the 12 plus 1. So now what can we do about that term? Because that term is going to be a little bit hard to deal with. So we can all apply difference of squares here, because now we're adding two squares. We're not really having the difference of them. So now, well, what does this really remind you of? What is 12? What is 12 a multiple of? Well, we already know 12 is a multiple of 2, but again, we can't use difference of squares. We also know that 12 is a multiple of 3. So if 12 is a multiple of 3, we know that 2 to the 12 plus 1 is equal to 2 to the 4 cubed plus 1 cubed, 2. So we see that not only is 2 to the 12 a perfect square, but it's also perfect cubed. So it can be expressed as a sum of two cubes, which you know how to deal with using our sum of cubes factorization. So this is just going to be 2 to the 4 plus 1 times 2 to the 8 minus 2 to the 4 plus 1 by the sum of cubes formula. And this is just going to be equal to 17, because 2 to the 4 is 16. And then this is just going to be 256 minus 16 plus 1, which is 241. Okay, now it's just a matter of a little bit of expanding out. So now we can just do this is equal to 7 times 2 to the 3 plus 1 is just going to be 9 times, this is just 65, or 5 times 13 times, and then 2 to the 12 plus 1 we found is just 17 times 241. So times 17 times 241. And then we can just put this in prime factorization form, we get this long number here. But we're not done yet. We want to find how many positive two-digit integer factors of this. So now, the idea is that now 241 is completely meaningless, because 241 times anything will always be way bigger than that two-digit number. So just ignore this completely, because it's not really giving us any two-digit numbers here. So now the idea is we do casework on the different number of factors. We can either have one factor. So if we're just having one factor, now what are the possibilities? So basically, if we're just multiplying, or I should say probably in a more easy way, 1 prime of multiplying. So if we're just multiplying 1 prime, how many possibilities are there? Well, if we're just multiplying 1 prime, well, we can see that the only primes that are two-digit numbers are 13 and 17. So if we're just multiplying 1 prime, then there's only going to be 13 comma 17, which means 2 ways. Right? Because there's only 2 primes that are two-digit numbers. Now, what if you have 2 primes? If you have 2 primes, now let's see the different. This is a little bit more of a tricky case. So now let's just look at the different possibilities. We can either have 3 times 3, but that's 9, so that's too small. It has to be two-digit. We can have 3 times 5, 3 times 7, 3 times 13, 3 times 17. We can see that these are all two-digit integers. 3 times 5, 3 times 17, they're all two-digit. We can also have 5 times 7, 5 times 13, 5 times 17. Those are all, again, two-digit numbers. 35, 65, 85. And now we also have 7 times 13. 7. But 7 times 17 is 119, so it's too big. And then finally, we also have 13 times 17, but that's, again, too big. 221, so it's not going to be a two-digit number. So overall, we have 1, 2, 3, 4, 5, 6, 7, 8 possibilities for this case. Now, the last case, 3 primes. Okay, so what we notice is that, what is the smallest possible value? You can have like 3 times 5, right? That's the smallest possible value, that's 45. So we notice that most of the time when you multiply 3 primes, it's going to be way bigger than 100. So there's very few possibilities you have to check here. 3 times 3 times 5 works. 3 times 3 times 7 also works. That's going to be 63. 3 times 3 times 13, that runs into a little bit of a problem, because now we see that the number is a bit more than what we need. So now this is too big. This is a 3-digit number, so it's too big. But we also can check that, maybe 3 times 5 times 7 will work, because that's the next, possibility. But that's, again, too big. It's 1 of 5, that's too big. So you can see there's only two cases in this case. So overall, you have 2 plus 8 plus 2. We have 2 for 1, 2 for 8 for 2, and 2 for 3. That gives us a total of 12, the answer for this problem. So just to summarize the key steps, the idea is we have 2 to the 24 minus 1. We wanted to factor it, because 2 to the 24 minus 1 is impossible to factor by hand. I'm sure if you actually tried that, you would run out of time before you could even finish it. So that would take a long time to factor, so we use the clever difference of squares and sum of cubes identity to get the prime factorization. And then now we have the prime factorization. Now we just check the different possibilities. We're multiplying 1 prime, 2 primes, 3 primes. And generally what a lot of people do, including what I used to do, is that when you have this big prime factorization and then you're just searching, you just randomly search, you randomly just write down whatever possibilities you can think of, and then you miss some or you overcount some. So that's why the best way to do it is do it systematically and look for whether you're doing 1 prime, 2 prime, 3 times, because this minimizes your chances of errors. Now let's take a look at the last problem. A positive integer n has a base 11 representation ABC and a base 8 representation 1BCA, where ABC represent not necessarily distinct digits. And you want to find the least possible value of n expressed in base 10. So basically, in simple terms, we have ABC base 11 is equal to 1BCA base 8, right? So how can we find the value of this? So your idea is you want to simplify this, because dealing with base 8 and base 11 is very hard to deal with, especially when you have these weird variables inserted here. BCA and ABC, we're like swapping the digits around. So let's just see what this is in base 10, really. This is going to be 121a, 11 squared times a, plus 11 times b, plus c. And this is going to be 8 cubed, so 512, plus 64b, plus 8c, plus a. So now what can we do? So of course we have these common terms. We're going to want to simplify this out immediately. So 121a, a. Let's make this 128 on this side. Okay? We have 111b and 64b. So let's make this equal to 53b plus 7c plus 512. So now what? Well, now we have 128 equals to this weird quantity. Note that the right-hand side is always going to be greater than this 512. Because clearly, 512 will always be there. So the right-hand side will always be greater than 512. Meaning 128 has to be greater than 512. So what's the minimum value of a such that 128 will actually be greater than 512? That's just going to be 5. So if a is 5, this is 5, then 120 times 5 is 600, which is greater than 512. So let's see. Okay, so if a is 5, does it work? Because we want to find the minimum possible value of n. So if a5 works, then we don't really have to check anything beyond that. Because we anyways want a minimum possible value of, let's say, ABC in this base 11. Okay, so a equals 5. Will a equals 5 work? Let's see. So if a equals 5, then this right-hand side becomes 600. And this becomes 512 plus 53b plus 7c. Or that means that 53b plus 7c equal to 88. Right? 600 minus 512. So does this work? Well, now that we've minimized, so we want to find the minimum a. So now that you look at the smallest a, we also want to minimize b first before c. So let's just check the minimum possible value b. So does b equals 0 work? So if b is 0, then this just becomes 0 plus 7c equals 88. But 88 is not a multiple of 7, so b equals 0 won't work. Now what if b equals 1? Well, b equals 1, then now we have 53 plus 7c equals 88. And that means that 7c is 35, or c equals 5. And well, that means that c is 5, and that does seem to work, right? Because now we have, if a is 5, if b is just 1, and if c is 5, we get a valid solution. And that does seem to be minimum, because we've minimized a, because it's the smallest possible value of a. We found the smallest possible value of b that works, and then c, we've seen that the value c that will let it work, because c matters less since it's at the end of the number. So now we just see, okay, 515 base 11. 515 base 11 is what in base? What is 515 base 11 in base 10? It's just going to be equal to 5 times 11 squared plus 1 times 11 plus 5 equal to, that's just going to be 605 plus 16, which is 621, the answer for this problem. And to summarize the key steps, what we did is we wrote this equation, then we wrote it in terms of the variables a, b, and c, then we simplified our equation, and we saw that the left-hand side, 128, has to be greater than 512. But then that means that a has to be 5 or more. So we just test a equals 5. And now we just look at the different possible values of b. So then you see, okay, if b is 1, if b is 0, then it doesn't work. If b is 1, then we found a valid solution of c, 2. So we found a, b, and c to be values, and then we can easily calculate the value of 515 base 11 from there. And that is the solution for this problem. Thank you all for watching this video. If you enjoyed it, be sure to subscribe to this channel, as there'll be many more math videos and you don't want to miss out on them.